Okay. How is everybody? You guys ready for Friday yet? Good. Giga Maggie's. She's got her Texas A&M shirt on. I have a brother that played football for Texas A&M. Oh, really? Yeah. It was cool. What he got on was pretty miraculous. He got recruited on his mission. So he was a pretty good high school football player, but from a small school in Utah. But yeah, crazy story. He ends up working out with some NFL receivers, like throwing the ball to NFL receivers in the offseason. And someone in the ward hears about it, calls up the A&M coaches and says, you should come take a look at this guy. And he ends up going down, playing wide receiver for Texas A&M for 3 years. So yeah, it's crazy, crazy story. But we thought, oh, it had to happen because he's going to meet his wife down there. He didn't meet his wife down there, but no, turned out well. Okay. Who'd like to start us off with a prayer? Thank you.
Dear Heavenly Father, we are very grateful for this day, wonderful weather we've been having. We're grateful for the opportunity we have together to work and to learn. And we pray that we will have the Spirit with us and that we may understand what we're taught. Pray for those who are currently quarantined, that they will all be healthy and will be able to get out soon. And we say these things in the name of Jesus Christ. Amen.
Amen. Thank you, and thanks for speaking very loud. So, let me see if Porter's on yet. Porter, are you on? Oh.
I am.
Oh, okay, good. I'll give you remote control access. What name are you under? I don't see you.
Oh, wait. I'm not your TA. I have the same name now.
Different Porter? Oh. So, that's okay. We love all Porters. So, okay. Well, those of you online, I don't have someone to run the controls, so I don't know how well this will go. So, if Porter Bagley gets on, you can yell at him. Okay, I'm just kidding. Okay, first homework over here, just the usual stuff, do the pre-lesson stuff for 3.2, then you can do the online homework for 3.1. Yes, you had a question?
I have a question about like the date for the first test, like on the schedule, one date, and then like due the date it starts on the schedule, and then like then something else says it's another date. So when is like the actual date?
We're still working that out. So the question is, when's the actual date for the exam? Because there's two different dates, different places. We're still working that out. So the content for this test will end next Thursday. So everything up through 3.3 is on this first exam, from what I understand. I'm working with the other professors on creating the exam. So yeah, in the past it's been material up through 3.3. So keep you informed. Sorry, I should have that nailed out already. Okay, other questions before we dive in? Yes. Like there's no 3.2 web assign?
Well, no, I'm saying like on my own page it says to do 3.3 also.
Oh, I don't know. I'll have to see. I'll have to go look at the schedule. So, yeah, there's very little on 3.2. Like 3.2 goes really fast. So maybe in the schedule, we have it so to do 3.2 and start 3.3. I'd planned to do that anyway. I didn't know we had a WebAssign already set up for that though. So I'll email you after class when I figure that out. Thank you. Can you tell I haven't been through this class before? This is my first time teaching linear algebra, so I'm figuring out some things just like you as we go through. Okay. this. And okay, so here's the important ideas from this section. And about 2/3 of these we can hit out in a minute, okay? Or 3 minutes maybe. You can add two matrices, you can subtract two matrices. You do that just by adding the corresponding entries or subtracting the corresponding entries. The key, you can't add and subtract any entries, I mean any matrices, they have to be the same size, okay? So, yeah, sometimes matrix operations aren't defined because sizes have to match up. So, okay, if I multiply a scalar by a matrix, what do I do? Yep, you just multiply that each number by the inside the matrix, each entry by that scalar. Okay, so 5 times 1, 2, 3, 0. That becomes 5, 10, 15, 0. Or 5, 10, 150. Okay. Just wanted to highlight that, be aware that sometimes the book will write just a big bold 0 to mean a vector of zeros, but sometimes it also means a whole matrix of zeros. So A plus B, I'm sorry, A minus A would be a 0 matrix if A is a matrix. So it would be full of zeros, not just the number 0, okay? We'll come back to this, we'll come back to this. A to the rth power, it's just a product of A times itself, R times. Okay, you've got R of those. What if you multiply A to the R power times A to the S power? What do you think you're going to end up with? A to the R plus S. If I have A squared times A cubed, then I'm going to end up with A times A times A times A times A. So I'm going to end up with 5 A's multiplied together. Okay? So A to the 5th power. How about A to the R times S? I mean A to the R all to the S power. That's A to the R times S. Because if I have A squared cubed, I'd have A squared times A squared times A squared. That's 6 A's all multiplied together. So A to the RS. Okay? And transpose. The transpose of a matrix, any entry Aij is going to go to Aji. Okay? You're not going to believe it took me almost a minute to write that down in the last class. But I got it this time. So what happens? So if I want to transpose this matrix, everyone write out or think about what that would be. I'm going to do another one here. What would the transpose of that matrix be? That one's not square. Okay. Okay. Let's do it. Yes. Oh. Good question. So thanks for bringing that up. A times B is not the same as B times A. You're right. But A times B times C, if we have 3 different matrices, oops, A times B times C, we can do, as long as we don't switch the position they're in, we can do the order in whatever way we want, okay? So it is associative, but it's not commutative, okay? So if you have all the A's there, you can do any A times an A, and you can take that times anything, or do some other A times A's, Yeah, you kind of pick and choose however you want to do that. Okay, good. Yeah, good question. Yeah, thanks. Other questions on any of these others? Okay, I'm glad you brought that up. Okay, so the diagonals stay the same because here we have A11, it goes to A11. A22 goes to A22, A33 goes to A33. What is right here? 4, so the 4 goes up. And what's right here? The 2. Right, transposing it flips it around this diagonal like that. So reflection along the diagonal. So this will be 7, this will be 3, this will be 8, this will be 6, and this will be 9. Another way to think about it is that our rows now became our columns. So the first row is now the first column, the second row is now the second column, the third row is now our third column. Okay, yes? No, it always works. Always works. Yep. So, oops. So this, if we do the row column thing, then our first row becomes our first column, our second row becomes our second column, and our second row becomes our third row becomes our third column. Okay? Or you can do the first column becomes your first row. Second column becomes your second row. Okay? So transpose, we're going to bump into a few different places. One of them is if you have symmetric matrices. So a symmetric matrix is where A transpose equals A. They have some really nice properties. And we're going to bump into those later on. They come up a lot in practice, like correlation and covariation matrices in statistics. They're always symmetric. So we'll study those a little bit. But also, it allows us to think about dot products in a different way. So if I have u and v, I can think about u dot v. We know how to do that. That's 1 times the 0, 2 times the -1, 3 times the 7, and you add all those products up. Okay? So I have 0, -2, plus 21, and then ends up being 19. Okay? Not bad.
Professor Corey?
Yeah.
Can you move the camera?
Oh, yep. Thanks for hollering.
Thank you.
Who is this?
This is Abigail Egan.
Okay, Abby, I'm actually going to give you remote control.
Oh, okay.
You're in charge conditionally. So,
All right.
and you should be able to move that mouse and click on the presets. So that would be the right whiteboard, maybe. Oh, that's right, whiteboard 1. Yeah. So you can play around with it, okay? You can make people sick. I feel like they're spinning around the room. Thanks, Abby.
Yeah, thank you. Yep.
Okay. Okay, so we can do the dot product, and but we can also think about the same thing as a matrix product. Yes. This bottom one, it's a 7. That's actually why I usually write my 7s. Yeah, it's a 6. It's a 0. So it's a really large 6, so big that it's equal to 7. So, but we can actually get this same thing as a matrix product. We'll talk about matrix multiplication in more detail in just a second. But if I had this times this.
Simon.
So if I have these, then, and I do the matrix product, which is I'm going to line up this row with this column and multiply those, and multiply the corresponding entries and add them, then I get 1 times the 0, 2 times the -2, and 3 times 7. And that is still the same thing. 1 times 0 plus a minus 1 times 2 plus 3 times 7. And that's a 1 by 1 matrix, and a 1 by 1 matrix is a real number. So, and so this is a matrix, this is with matrix multiplication. But to write this, I have to write it down as U transpose V. So see, I take my U, I transpose it to this, and then I can do that multiplication, not the dot product. Now this is matrix multiplication. So we can write down, we can go back and forth if we're just talking about vectors. We can write down the vectors, we can write down this as a matrix multiplication, or if they're both vectors, we can just write U times V. Okay? We're going to use this. I didn't get to it in my last class, so I doubt I'll get to it here too. But next time, we'll start solving an equation that'll be really helpful to solve, and we're going to end up having to use that. Okay. Questions about transpose?
So technically, if the U is in that dimension, the V is in that dimension, we could multiply it, or we're just writing it. Because like if U was 1, 2, 3, and X, and the V was the 1, 2, 3, and Y. So technically we can't do that, but we're just writing it as.
Oh, like, do you mean just like U times V where this is matrix multiplication? Can you just do this?
Yeah, I guess I'm wondering why we have to write it as UT.
Okay, so yeah, if we have these two vectors like this and we want to multiply them, not dot product, just matrix multiply, this is undefined. We can't do this. So, but why? Let's talk about matrix multiplication in general, and then we'll come back to this. Okay, because yeah, this is getting right to where we want to go. Yes. Why would you ever take the transpose? Well, we'll see a situation next time where we will take a transpose when we're trying to solve an equation, okay? But it does change. Okay, I'll give you an example. This is kind of on the fly, so we'll see how well this works. Apparently it's not working very well. So we did have peanut butter, bread, and we'll say jam in a matrix like this. And here's our nutrients. Okay, nutrient 1, nutrient 2. This answers some questions. We might multiply this to figure out some questions. But another question you might ask is, how do the nutrients impact things? So I could say nutrient 1, nutrient 2, I could even have more, nutrient 3, we could have more nutrients here, where I have peanut butter, bread, jam, and I could keep on going. And this is the matrix I would use to say something like, how do the different nutrients impact calories? And I want to answer that question instead. This one answers, how do my servings of each impact my total nutrients? So they just answer different, you can answer different questions with them. So, okay. Good question. I don't know if that was the most compelling, but that's what I can come up with off the top of my head. Okay. All right, let's talk about peanut butter book. One reason I wrote the peanut butter book, at least so far, is because you probably had the same experience I did if you've had a unit on matrices before. And when you got to the point where the teacher was going to teach you how to multiply matrices, they gave you some matrices. And they said, okay, the way you multiply matrices is you take this first row right here and you think in your mind you're going to move it like this. So you're going to match up that 1 with the 5, the 2 with the 2, and you're going to multiply those things. So the 1 times the 5, and the 2 times the 2, and you're going to add those together, so you get 9. And then you can do the same thing. You take this row right here, and you're going to think in your mind, you're going to turn it around sideways. You're going to get the 1 times the 1 and the 2 times the -3. So, and then you're going to add those together. So that's 1 plus a -6. And that goes in this spot because it's in the first row, second column. And what was that? A -5. Okay? Is that what your teachers did? Yeah. And it's like, I remember sitting there like, why in the world? Who came up with this? Like, mathematicians really bored and they just want to torture students? And I'm like, why in the world? So I didn't want students to have that same experience I did. So I tried to, I thought, if you think about this in a context, it should play out pretty straightforward on why we do it. And it does. If we go back to, I don't know if these were the exact values. Okay, if we're taking combinations of the nutrients in peanut butter and bread, okay, these are servings. Right here, this is 1 serving, this is 2 serving. This is serving of peanut butter. This is peanut butter. This is grams per serving of fat, grams per serving of protein. You're right, I got them mixed up. Protein, fat, there. So this is kind of the protein line. This is the fat line, okay? And this is grams per serving of protein for bread. And this is grams per serving of fat for the bread. And so the units work out really nicely. So here we have, this is servings of peanut butter. This is 16 grams of serving per peanut butter of protein. And so you multiply the units, the dimensional analysis is what they'll call it in science. If you work on the units, you end up, well, that's going to give me grams of protein. Okay, so I have grams of protein here. I do the same thing here. I'm going to end up with grams of protein. I end up with 16 plus 16, which is 32 grams of protein. And then here I have servings of peanut butter. This is 10 grams of serving per peanut butter of fat. This is 1.5 grams of serving per bread of fat. So, and this is 2 servings of bread. And you do the multiplication and you get, this is total grams of fat from the peanut butter, total grams of fat from the bread. And what do you get with this one? 13 grams of fat. Okay? So the units work out, when you think about it this way, very nicely. It's just that the notation, often it's nice to think about these 2 numbers also as a packet. We want to think about them also as a vector. So the way we end up writing this, that's like the favorite sound of it for a teacher. Ah, that makes sense. Yeah. Well, that was so cool. You know, I'll take that too, you know. So now I forgot what I was doing. Yeah. So 1, 2. So we write these servings as a packet. So this is the serving packet. Okay. This is the food. This is the food and nutrient matrix. Okay. So this is, I'm not going to write down all of the units again, but this is servings. But this is 1 serving of peanut butter. This is 2 of bread. And we want to end up with this is total grams of protein, total grams of fat. I put G there. Maybe fat gets translated into gluten somehow with this multiplication. And so so you can do what your teacher said here, right? 16 and 8 I twist that, I get a 16 times a 1 and 8 times a 2. I add those together, I get 32. But where that came from is really, I'm thinking of 1 serving of this column. And I'm thinking of 2 servings times this column, and I'm adding them together. You're just breaking it up in an easy way that's a little easier to do the computation. Okay? Questions about this? Like why we multiply matrices the way that we do? Yes?
Is there a way to like help remember, because like for instance, A times B is different than B times A. So is there a way to help remember like, okay, if it's A times B, I'm taking the columns of A and the rows of B.
Yeah, you always do the, if you do this process, you're always adding together the rows times this column. It's whichever's on the left, it's always the rows, and you match it up with the column. If you're not sure, you can always write it out as a system of equations, because if you think about this as x and this is y, then you're going to have 16x plus 8y equals whatever over there, and this is 10x plus 1.5y equals that thing, and here y is 2 and x is 1, and then it tells you what you're supposed to do. Okay, so it's also, I mean, the other place where it comes from is it's just the math of the computations that come from the system of equations. So it's just this thing gets turned sideways. Excuse me. This thing gets turned sideways to make it easier to work with, and I think there are some of the other reasons, but yeah. Did that help? Yeah. Yeah, so you always go rows, column. Or you can do it this way. You can go here to here, and that corresponds better. I exercised hard yesterday for the first time in a long time, and my lungs are still recovering. So I went running with another professor. He was on the track team. He and I were both on the track team together here. But he actually ran track. I threw the discus. And the other guys that I was going to run with didn't show up, so I went with him, and I kept up with him for maybe a half a mile, and then I just slowly jogged back. That's like all I could do. Okay. Fun story about this guy. He was second place in the 800 in Canada. So he was almost the national champion in high school. He came to BYU. He said, I found out that the national champion in Canada is not even a state champion in Utah. So just thought it was funny. Okay. But this is a matrix times a vector. What if we have a matrix times a matrix? What did someone say? So 16, 8, 10, 1.5. This is 1, 2. This is Jones. This is Jones' servings. This is Tyler's servings. And this is Sarah's servings. Okay. You might think, how do you have a -1 serving? Well, she was already eating bread. She's just lowering. This is the change in servings. And then we can throw in some negatives. But okay. So peanut butter, bread. This is protein. This is fat for this one. But this is servings of, this is peanut butter here. And this is bread. This is servings of peanut butter. This is servings of bread. So once you write out the units, you see what has to go together. Like these, the peanut butter and bread better match up with peanut butter and bread. So, so how are we going to do this? So you can either think about it this way or think about it this way, just for doing the computation. So 16 times 1, 8 times 2 gives us our 32. And now for the second entry, so for Tyler, how much? Oh, we should really write out, maybe we should, it might help if we write out what we're going to end up with. This is Jones, this is Tyler's, this is Sarah's, and this is protein, and this is fat. This is going to be the total amount that Joan has in those two categories, the total amount that Tyler has in those two categories, and total amount that Sarah has in those two categories. So this better makes sense. Servings for peanut butter, servings for bread, match them up for protein, peanut butter and bread, then it has to be on the protein, and it has to be with Joan. So it's got to end up with right there. So Joan, fat amount, so she had one of these, two of these, and so that's the total amount of fat for Joan. So it goes in the Joan and fat entry. So for Tyler, is 3 peanut butter, 1 bread, so he's going to, every serving of peanut butter, he has this much fat, I'm sorry, this much protein, bread this much, so 3 times 16, 1 times 8, I think it's 56. And then 30 plus 1.5 is 31.5, and then Sarah, we have 80 minus 8 is 72, and here we have 50 minus 1.5, so 48.5. She already has a diet where she's eating some. She's just lowering the amount that she's eating. So, yeah. So it's really not servings. It's the change in servings. So once you do change in servings, then you can have negatives here. So still hard to have negatives here, right? What food has negative protein? You can have. There are foods that have negative calories. It takes more for your body to digest, more energy for your body to digest than you get out of it. So you can, yeah, there are foods that actually have negative calories. So I read it online, so it's got to be true. Okay, all right. Any questions on why we multiply matrices and vectors the way that we do? Okay, good. My work here is done then. If all you get from this class is you understand why that you multiply those things, then good. So what is happening when we multiply a matrix times a vector or a matrix times a matrix? That's what we're going to talk about next. One way to think about matrix multiplication is it transforms vectors. And what I mean transforms is it, oops. So when we think of multiplication with just a vector on a number line, we can think of the multiplication transforming it, right? It can stretch it. So 3 times 2, this is the 3 vector. Really, that's 2 times 3. Okay, 2 3s, it stretches it. I end up with 6, right? I can think about one vector now that points to 6, or I can think about 2 of them end to end, but I can think about one of them. It changes the length, okay? It can also change direction. If I take a -2, okay, then I could end up this way, right? It changed directions. It's now going negative, and it changed the length. Matrix multiplication of a vector changes the lengths and directions of that vector. It's easy to see. It's easier to see on the plane, but it works in n-dimensional space. Okay, but there's a lot more ways to change than just going this way or this way when it comes to direction. So if I have a vector 3 1, okay, I can 8. That can point infinitely many. Yeah, I mean, I've got infinite directions. Any angle you tell me, I can point there, and then I can change the length. Maybe technically you could say maybe it only changes half that, because that's really all you need, and then negative values get you your other one. But but we can't just change that we can't get all of those with just a scalar multiplication. scalar multiplication, I'm just going to be living on that line. You need something more. And these 2 by 2 matrices that I would multiply by this, it allows us to transform this and point it to anywhere else in the plane. Okay? So to play with this, okay. Can everyone see this all right? Oops, I didn't mean to do that. I was just trying to make it bigger for you guys. Okay, so here we have the picture of whoever this kid is, Bart Simpson, and it's going to take every pixel of this picture, and it's going to multiply it, every coordinate of the picture, and it's going to multiply it by this matrix T, 1, 0, 0, 1. Okay, and then it's going to, when we can change the values of this matrix, and then as we change the values, it will show us where all of those pixels go to in the image. Okay, so I'm going to change A. I'm going to move it up to 2. What do you think is going to happen to the picture? Think just for a second. What's the what? This. A, B, C, D. So for those of you that are on the, oops, wrong one. There, so A, B, C, D. No, that's not working as well. Okay. One way to think about it is 2, 0, 0, 1. If I multiply that by any point x, y, any coordinate x, y, then where is that new point going to go to? 2x, because I have 2 x's, 0 y's. That's my new x coordinate. This is my new x coordinate. And what about my y coordinate? I have 0 x's, 1 y. So my y coordinate stays the same. For any value then on the picture, the y coordinate's going to stay the same, but what's going to happen with the x coordinate? It's going to be twice as large, so I'm going to stretch it out to the right twice as much. Okay, is that the case? There we go. Come on, guy. There's 1 up to 2. Okay, so it did. It stretched out twice as far to the right. Okay, what do you think is going to happen if I change D? Right now the D is 1. It's that lower right-hand corner. I'm going to move it to 3. So what do you think is going to happen? Okay, 3 times as tall. Okay, what do you think is going to happen if I change C? Crazy things start happening here. So you can flip him around so he's looking the other way. Okay, you can twist. Okay, all sorts of things. Okay, I want you to tell me what 2 by 2 matrix, what ABCD will rotate the picture 90 degrees to the right. So 90 degrees counterclockwise. Okay? You guys can work with your neighbors while you do this. Okay? You can figure that out.
You want to stretch around the negative y-axis now? Is that rotating around the origin or rotating? Which means we'll want it first. In the y coordinate. Oh, exactly.
2, 0, is the first XY coordinate. 0, 1. Is it rotating about the origin or is it going to be becoming?
Oh, it's rotating about the origin. So good clarification question.
Yeah, we want the two elements.
So that's what's happening. So you have the ABCD and then matrix multiplication. So
So right now,
All right, anyone got a guess or figured it out? In the last class, I had someone pull up the computer and go to the website and play around with it. So, anyone have an idea what the 2 by 2 matrix might be? Yeah. 0, -1, 1, 0. How'd you come up with that?
I wanted the x-axis on the negative y-axis, and the y-axis being the positive x-axis.
So you're thinking about like x. How do I want my x's and y's to change a little bit? So you're thinking, I want points here on the y. Hold on. So everyone can see us. Nope. Now I need to go to my. How do you move to this? So it's in front of a screen. So
Use the manual controls, maybe?
that's weird. You'd think there'd be a preset. Wow. Believe it or not, so what you're seeing here is repeated matrix transformations, repeated multiplication of a matrix to produce all of those, or we could produce those. So, okay, but let me pull up the website here. Okay, so you're thinking, I want the values here to come over and be the same values as I have over here, and the values that I started here, I want them to be the negative values that they started with, okay? So is that what we get with these? Here, I'm just going to change it to that, and we'll see. So A is 0, and B is a -1, and D is, C is 1, and D is 0. So you are close. You have a rotation counterclockwise, 90 degrees. So, yes? Okay, hold on. Let's look at this one, then we'll go to your next one. Okay, so let's see what's happening when we multiply this. Any coordinate on here is going to go to, my new x coordinate is going to be minus whatever my y coordinate was. And my new y coordinate is going to be what my x coordinate was. So if your x coordinate was 3, that's going to be my new y coordinate's going to be, if your old x coordinate was 2, your new y coordinate's going to be 2, so it's going to be along this line. And if your old y coordinate was 3, your new x coordinate's going to be a negative 3. So it goes that way. Okay, very close. And you were suggesting how we could change this? Now, yeah, we hopefully we can think about, yeah, we want our y to be our new x value, right? So if I'm 3 up here, that should be end up being as this coordinate 0, 3 should be 3, 0. And my x coordinates are going to be negative, will be the opposite of those will be my new y coordinate. And that's what I get here. I get y and a negative x. And is that what happens? So yeah, nice job. Okay, very nice. So one way to see that, if you're comfortable thinking about, oh, an arbitrary xy or a particular xy, you're going to transform. This is one way you could do this. I was not really good at thinking that way when I was in your shoes. I'll tell you what I was good at, though. I was really good. I was marginally good at throwing the discus. So the problem is I looked more like a long jumper or a high jumper, but now left 1 maybe, left 2. Okay. I was really good at thinking, okay, I know I just need to find A, B, C, and D. And if I rotate to the right, then my point, the point 1, 0, the vector 1, 0, that's x is 1, y is 0, so it's going this way. It needs to go to 0 or minus 1. So I would just pick points, and I can set up a system of equations. And I'd pick another point, because this actually tells me something, but it doesn't tell me everything. So here, if we multiply these out, what does it mean? That means I have 1a plus 0b, 1a plus 0b equals 0. And 1c plus 0d equals a minus 1. So I already know what a and c are, 0 and a minus 1. And a, b, c, d. If I multiply that matrix by 0, 1, so that's the point 1, 0, so I'm 1 up on the y-axis. Where does that go to? That goes to 1, 0. And so this says that b, I get 1b, no a's, has to equal 1. And no c's, 1d equals 0. And then that just tells me what all my values are, a, b, c, and d. Now, you can still do the same thing. Luckily, we could pick nice values that made the systems of equations very straightforward. We didn't have to do a lot of solving or any solving. But I could have picked different points on the picture. I'd know the point 2, 3 goes to a negative 3, 2. I'm sorry, 3 and a negative 2. And you just have a more complicated set. But this is what I was really good at. I could just start with A, B, C, D and start thinking about where points are going to go, and then I can start solving. So, more straightforward approach. Okay. So now my question for you is, what would this represent? Okay, so that's not the one. So this is rotation to the right 90 degrees, okay? So what is 0, 1, minus 1, 0 squared? Not only just what is it, what rotation, what transformation is that? So you guys can work on that. We don't have time to work on it. Any guesses on what this does? Right, you can't just square 0, square 1, square minus 1, and square 1, right? So that would be 0, 1, minus 1, 0, 0, 1, a minus 1, 0, going, 0, I'd have 0 minus a 1, I'd have 0, 0, I'd have here a minus 1, there I get 0, and here I get a minus 1 times the 1 plus a 0, so I get a minus 1. So that's what I'd get. What does that do? So 1 is a minus 1, B is 0, C is a minus, C is 0, right? B is a minus 1. Yeah, so it's a rotation of 90 degrees twice. So which is a rotation of 180 degrees. So. No, you'd get something different if you reflected over the line, right? If I reflected over the line here, these clouds would be on this side. So, right? So it's twisted. All right, have a great day. You should think about what would happen if I made the columns of the matrix linearly dependent. What's going to happen to the image? So, you're welcome. Another thing I love to hear from students.